Hello and welcome. My name is Stephanie Winwood and I'm the Head of Investor Relations at Blue Glass. On behalf of Blue Glass and Share Cafe, it is my pleasure to welcome you to our fourth Expert Roundtable, where we bring together sector experts from around the world to discuss global trends, opportunities, and challenges driving innovation in the semiconductor industry. In today's session, the gallium nitride revolution, powering the technologies of tomorrow, we are discussing the essential and highly strategic compound semiconductor, gallium nitride, also known as GaN. Semiconductors will be a US $1 trillion a year market by the end of the decade. They are the oil of today's technology era. And as the electrification, digitalization, and decarbonization transition continues, silicon is running out of gas. Gallium nitride semiconductors are the next generation rocket fuel, driving advanced technologies and capabilities around the world. GaN's benefits are myriad. We have greater efficiency, faster power switching, smaller size and weight, and now lower cost. GaN is changing the way we move, the way we work, and the way we live. I'm joined today by a stellar industry cast to unpack gallium nitride's growing role in enabling critical capabilities and driving global megatrends. Everything from advanced computing and AI, advanced manufacturing, Industry 4.0, defense and aviation, to decarbonization and the energy transition. It is my pleasure to introduce you to Professor Stephen Dunbars, an industry luminary and Professor of Materials at the University of California, Santa Barbara. He's also co-director of the university's Solid State Lighting Center. Professor Dunbar's pioneering work in GaN-based semiconductors and the application to blue LEDs and lasers has led to more than 800 scientific publications and over 160 US patents on electronic materials and devices. An IEEE fellow, he co-founded Sora Laser Diode, now Kyocera SLD, and has served in advisory roles for Cree, Seoul Semiconductor, and Hewlett-Packard. Thank you for joining us today. We're also joined by Dr. Michael Schutte. He's the Director of Business Development at MACOM, where he's responsible for incorporating evolving customer demands into corporate technology strategy. He has held technical leadership roles in industry and with the US government, yielding breakthroughs in millimeter wave GaN transistor performance, development and execution of defense technology programs, leveraging compound semiconductors, and adoption of emerging RF devices in both commercial and defense systems. Prior to a recent corporate acquisition, Michael was with the RF business unit at Wolfspeed. We're also joined, and I'll have to get you to correct me on my enunciation if needed, Dr. Hugues Marchand, who is currently VP of Epitaxial Technology at IQE and oversees new product development for GaN electronic and optoelectronic products. With a background in engineering physics and a PhD in electrical and computer engineering, he has held various technical roles in early stage and mature companies throughout his career. Hugues has been involved in process development, yield improvement, data systems, project management, and technology transfer for compound semiconductor products such as lasers, LEDs, and transistors.
Thank you.
I'm also joined by Dr. Stephen Duval, who is an independent semiconductor professional with more than 40 years semiconductor industry experience, completing his PhD at Stanford University in 1983. He spent almost 2 decades with Intel in California, driving corporate initiatives in design for manufacturability, and a further 6 years with Intel in Australia, supporting Intel capital globally with technical and commercial due diligence and entrepreneurial companies. He is the former Chief Technology Officer and General Manager at Ultraviolet Products at Solana Semiconductor, an Australian developer and manufacturer of advanced semiconductor components where he spent 14 years. And finally, we're also joined by Blue Glass's own Dr. Josh Brown. Josh is a 3-nitride materials and device professional, contributing to novel device structures and demonstration in GaN LEDs, micro LEDs, laser diodes, and power electronics. During his time at Blue Glass, Josh has been heavily involved in equipment and process development of the company's core RPCVD technology. He's authored a number of publications and is a named inventor on several key patents. Thank you all so much for being here today. I'm going to open the panel with a question for Professor Dunbars. Semiconductors are the single most important technology on the planet and enable all other technologies to think and function. Gallium nitride is a wide bandgap semiconductor with many key advantages over traditional silicon semiconductors. Can you explain for the layman investor why GaN is touted as the most important semiconductor material since the advent of the silicon chip?
Sure. Thanks, Stephanie. So first and foremost, gallium nitride is a semiconductor that emits light, and that's something that silicon can't do. So because it emits light, we can use it to make LED light bulbs, which now everybody has in their house. But that ability to make light also can be used in a laser, and so we can do communications with it. We can do blue, green, and eventually even red emitters with this, so we can make displays. So a lot of the next generation displays will be based on lasers or even micro LEDs, which use this ability to emit light. But just looking at it as fundamentally different material, it's able to handle very large currents and very large voltages in comparison to silicon. And so that's why we think it's the next thing, because now we can start using these chips that run at high voltages and high power in things like power adapters, in electric vehicles, and even in high-speed communications, because the electrons move faster in gallium nitride. So those are some of the semiconductor material properties that make it particularly attractive to kind of being the next most important semiconductor material.
Yeah, thank you. So it sounds like it's enabling lots of technologies that weren't possible even a decade ago. Can you enlarge on what kind of new applications it's enabling?
Oh, sure. So, one of the things it's enabled in the way of lighting is the ability to now make light bulbs that can communicate very quickly. So that's something we call light fidelity communications. So not only can your cell phone talk to the light, but the light can talk to you. And so we can do things like adaptive lighting. We could change the lighting color or the quality to your preference. That's something new that you could do with the light. In the power electronics area, it's reduced the size needed and the amount of cooling you need for certain things like power adapters. So we're able to get very fast power charging and very high power charging in a very small space. And that's let us make power adapters much smaller. So they're just two of the applications.
Amazing. Thank you. My next question is for Michael. MACOM is a global leader in high-performance semiconductors. Can you tell us a little about the company and in particular your role in pioneering compound semiconductors?
MACOM has been innovating in RF, microwave, and optical technology for over 70 years, really. The company pioneered semiconductors for RF applications. MACOM powered the first space missions into solar orbit and also to Venus.
Amazing.
And also MACOM was the first to develop RFICs for mobile devices years ago. We do semiconductor wafer production domestically in the U.S. in three main locations in Massachusetts, North Carolina, and also Michigan. And we have a global design and sales footprint. We leverage our core competencies, which really span from material science all the way up to subsystems in service of three key markets. The first one being industrial and defense, followed by data center, and then telecom. So MACOM products are based on a wide range of compound semiconductor and silicon wafer processes in a variety of packaging technologies. And with a number of recent acquisitions, including, like you mentioned in my bio, Stephanie, the RF business unit of Wolfspeed, we've become a leading supplier of gallium nitride, RF, radio frequency components, and also foundry services, with an extensive GaN on silicon carbide portfolio and over 20 years of GaN experience. So as far as my role as a business development director, I spend a good deal of my time with our customers, in particular those in the Department of Defense, science and technology community, interpreting evolving system requirements and how those can be addressed with MACOM's existing and future products. And then, of course, working internally across our company to ensure any new technology or products are ready in time to meet their demands.
Awesome. And so coming back to it, what are the applications driving adoption of GaN semiconductors, and where is MACOM focused? Is data centers moving to GaN?
So for the data center, the gallium nitride in applications would be in the both the a big application for GaN would be in the power systems that enable the data center. Data centers are very power hungry, and some of the wide bandgap semiconductors, including silicon carbide, but also gallium nitride, are forming the solution to that. But in the industrial and defense sector, you've got radar applications, EW communications, things like this, where you need very high power densities, but also high power efficiency from the gallium nitride. And then for telecom, this is for the base station infrastructure. So the power amplifiers that drive the transmitters for those applications.
Thank you. Oog, I might turn to you now. In your role at IQE, you lead epitaxial growth of GaN semiconductors. Can you give us an overview of what epitaxy is and how gallium nitride is made?
Yeah, sure. Thank you, Stephanie. So epitaxy means essentially assembling layers of a material. In this case, we're interested in semiconductor materials by adding essentially atoms on top of existing atoms, right, an underlying material, while maintaining the underlying structure of the crystal, the starting crystal. This allows us to have extremely precise control of the composition of the material, as well as the thickness of the material. And in turn, we can also create very sharp interfaces between different compositions. Essentially, this enables functionalities that are just not possible in bulk materials. I'll give you a couple examples, just one example, really. So we can make a well and a barrier material to form a quantum confinement structure. And that's the heart of all the devices that we've heard about so far in this discussion. It's lasers, LEDs, transistors. And so that's the essential reason for using this process. We also call this process crystal growth. So there's different flavors of it, but essentially at atomic level, very sharp composition and thickness control.
Amazing. So silicon chips require hundreds of manufacturing and process steps. In comparison, GaN semiconductor growth replaces the majority of these manual steps with that pretty exquisite atomic science that you're talking about. Can you explain the importance and value add of epitaxy, both in terms of improving device performance and in streamlining manufacturing and reducing production costs?
Yeah, that's a great question. So in the compound semiconductor, I think we might agree all on this panel that we like to say the performance is in the epi. This is kind of that's your point here, essentially. So the functionality of the device is created by the material itself, the compound semiconductor material, or by the layer stack of compound semiconductor materials that we combine in the epitaxy process. And this is very different than silicon industry, where the performance essentially comes from the miniaturization of the silicon material, right? Essentially Moore's law. And don't get me wrong, the design is also important for gallium nitride devices, and the materials, of course, are very important for achieving the performance that silicon has achieved today. But as a whole, the performance originating from the compound epi, I think holds true across the board. And so in terms of cost, how does that connect to the cost? One thing you can think about is that with the intrinsic performance, let's say, of compound semiconductors, including gallium nitride, and perhaps specifically gallium nitride, you can make cutting-edge devices using a fully depreciated silicon factory, for example, which is a very different case than top-of-the-line silicon technology, where you need gradually more expensive fabs in order to reach that level of performance. So it's fundamentally a different equation.
Yeah, that's huge, actually. It's quite amazing. Thank you. My next question is for Steve Duval. You have spent much of your career developing novel semiconductor applications, including pioneering ultraviolet GaN semiconductors. What are the applications for these UV semis, and how will this revolutionize medical and biotech applications?
Okay. This work was done at Solana Semiconductors here in Sydney. And we were developing UVC light emitting diodes, LEDs. And these are manufactured using GaN and another material, aluminum nitride. And they're similar to conventional red, blue, and green LEDs. They just emit UVC light. And for those of you who don't know, UVC is below UVA and UVB. So you'll be familiar with UVA and UVB with sun safety considerations. This is just a shorter wavelength. And there are really two broad areas of application. The first is in disinfection, and the second is in sensing and measurement. Now, how does this work in disinfection? And UVC light is a universal germicide. It means it will kill any germ, virus, bacteria, fungi, algae, whatever it might be, with sufficient exposure to the UVC light. And the advantage of using an LED versus a more conventional UVC lamp is that they're compact, they're robust, and we can adjust the wavelength to suit the particular application. The power requirements are much simpler, so the power supplies are simple. So effectively, UV LEDs allow UVC light to be deployed almost anywhere. So we have a universal germicide combined with the ability to put it almost anywhere. And we're starting to see this, that UV LEDs are being rolled out into water treatment systems, into appliances. I see refrigerators with them, air conditioning units, things like that. So it's allowing this sort of disinfection to be more broadly deployed and deployed in a very effective and power efficient manner. And the second application is in measurement and sensing. And the main advantage here is it allows you to expand the range of substances that can be easily detected. So the idea here is that with UV LEDs, we can develop point of care biosensors that can diagnose diseases, detect viruses and bacteria. And devices can be built around UV LEDs that can be used to monitor pollution levels in fresh and salt waters, monitoring contaminants in drinking water, things like that. So they have a very broad range of applications, both in almost all in human health and environmental.
Yeah, it sounds like it's going to be hugely beneficial, especially when things like antibiotic resistance is on the rise. So yeah, it's really crucial. Just want to remind our audience that you can post questions to our panelists in the Q&A box, please. My next question is for Josh. Blue Glass is focused on turning its gallium nitride semiconductors into visible lasers. Laser technology, largely based on invisible infrared technology, has been around since the 50s. And like semiconductor technology, underpins most advanced technology capabilities around the world today. However, GaN lasers are an important emerging technology. What are their unique advantages?
Yeah, thanks, Steph. Look, there are many unique advantages. I think we got heard some of those properties from Stephen Dunbar, but in terms of lasers, let's focus on a few of the key ones. One of the major ones is wavelength. So GaN-based laser diodes are able to emit in visible wavelengths, so all the way from ultraviolet up to sort of green wavelengths, it's around 530 nanometers. And that opens up applications, for example, in visible light communication. So this is where we need to be able to see the light because there's some practical purpose for that. Perhaps it's lighting up our room or something like that. But then that light itself can be used for the communication, for the actual transfer of information. Any visual application, so projectors, things where you need to be able to see the light. GaN opens up a window into devices where you can see these visible applications. A really interesting one is quantum applications. So quantum applications is a pretty hot topic at the moment. In a quantum application, you want laser light to interact with a specific atom. And there are many different atoms that are of interest in the quantum space. And how you interact with that atom, it's got to do with the structure of the atom and what sort of energies are involved. And you need to be on resonance with those energies. That means you need the wavelength of your light to have the same energy as that transition in the atom. And there are many that are of interest around things like quantum clocks, for example, that require wavelengths in the visible spectrum. So all of those applications are looking at a visible light. So that's all about the wavelength that gallium nitride and those material systems open. Another really interesting one is the efficiency. So again, we've heard that GaN is extremely efficient. And what that really means is you get a lot of bang for your buck. You put a small amount of current in, you get a lot of photons out. That means you can use applications that require very, very high power, but also you don't need much power to drive those devices, so they don't generate much heat, and they can be used in applications where portable applications, for example, where maybe you want to run them off a battery, for example. You don't need a large power supply. They're small and they're compact. Anything that needs to be has a small footprint. Medical devices, compact projectors, for example, they might have size requirements, and GaN-based lasers are able to fit into these smaller packages. And another really interesting one is lifetime. So gallium nitride is very, very robust, thermally and chemically stable. That enables you to drive these devices at very, very high powers for very, very long periods of time without material degradation. So all those sort of applications, gallium nitride is opening up.
Amazing. Thanks, Josh. I will just say that the Q&A box was disabled. Apologies. It is now enabled, so everybody should be able to see that there now. Thank you for bearing with us. My question now is again for Professor Dunbars. One of the major ways that we rely on GaN today are photonic devices, in particular lighting. And you've predicted that the way we interact with light, and you've indicated this a little bit already, but that it will radically change in the decades ahead. Central overhead lighting systems and the need for extensive copper wiring may be a thing of the past. Can you tell us more about this potential?
Yeah, that's kind of called basically doing light fidelity communication. So that's the potential is we could probably get away with the copper wires because GaN LEDs can be powered with very little power at low voltages. So that's called power over Ethernet. So you just plug in your Ethernet cable into your light bulb, and that lets you do both data and power. Now, believe it or not, the need to switch the gallium nitride LED or laser on and off very quickly is a huge advantage in communication, because now we can start doing gigabit level light communications. And this won't just affect lighting. This will also affect what you had touched on, the data servers. So we're looking at it for what's called AI communications, because we can do vast arrays of these micro LED gallium nitride micro LEDs at fairly low cost, and they can all transmit data up to a gigabit per second. So having an array of these small GaN light emitters will let us do terabits per second of a communication, which very low power, which is the need that we're all seeing is being driven by artificial intelligence, is having huge communication, but also huge power requirements because it's primarily being driven by copper. So that ability to replace copper wires with light is going to be big.
That is mind-blowing, some of the things that you've just said. The terabits per second and also data and power from your light bulb, that is going to radically transform how we use technology in our homes and lives today. Another one that I wanted to talk about, though, is actually the energy transition. Could GaN or GaN lasers play a role in enabling nuclear fusion?
Okay, so that's one of my colleagues, Professor Nakamura, is working on that. So I think that's a little farther out, but that eventually, as you know, they have demonstrated laser fusion with frequency tripled lasers, which rely on these old big diode pumps. But he's trying to miniaturize it because both the UV and the blue light can be used to create fusion reactions with hydrogen to create helium and release huge amounts of energy. I do think eventually this will be possible. This requires us scaling up the lasers from where they are today, which is hundreds of watts, into not just kilowatts, but we need megawatt lasers to do these kind of things. But along the way, there's other low-hanging fruit in what I call driving chemical reactions. So we can use GaN lasers in particular, and even what Stephen Duvall mentioned, UV. You can use UV and blue lasers and LEDs to drive chemical reactions. So not just laser fusion, but we can do photochemistry. So as you know, photosynthesis is light-driven chemistry, and it uses visible light. It uses blue and red light. So we can do the same things now, not just for photosynthesis. So that's a huge growing area, is looking at using these GaN light sources to drive chemistry reactions.
Amazing, thank you. That's very exciting. Michael, my question is for you now, and it's turning a little bit towards policy. The US $280 billion Chips and Science Act was established to reshore advanced semiconductor manufacturing in the US. And since its launch in 2022, key manufacturers such as the world's largest producer, TSMC, and Samsung have announced large-scale fab builds in the US. How do you see the Act working to stimulate the US sector and economy?
Everybody's excited about the CHIPS Act. The circles that I run in, it is incentivizing, construction, expansion, modernization, manufacturing along the entire, U.S. semiconductor supply chain. It's also supporting research and development under programs like this NSTC, National Semiconductor Technology. And there's an advanced packaging program under the R&D umbrella. And the CHIPS Act is also placing special emphasis on the underlying workforce. Some major workforce gaps have been identified, and that's kind of a centerpiece of what they're trying to pull off here. As you mentioned, CHIPS seems to be motivating a number of companies to announce new, fab construction in the U.S. And in this way, the act is stimulating the U.S. economy. And I can say over the next 5 to 10 years, we'll have a more clear basis to judge, just how successful it was at meeting the intended goals.
Yeah, thank you. You touched on the R&D side of things, and I actually just want to now turn to talking about some of those key megatrends and the applications that are driving next-gen semiconductor manufacturing, and also what role GaN plays in these applications and megatrends.
The thing about AI is that it not only, places strong demands on the hardware that it runs on and the supporting infrastructure. For example, from a data processing, interconnect perspective, as well as, like I mentioned earlier, the power delivery systems for these, server farms, data centers. But it's also starting to find its way into the modeling, design, and manufacturing of the semiconductors themselves. This is pretty early stage stuff, but we're definitely going to see it as the years go on here. The second one I think I'll call out is related to wireless networking, right? So this includes 5G, 6G, or future G is a term that's starting to be used in some circles, as well as the Internet of Things as everything becomes more connected. So what role does GaN play? Well, GaN, HEMT technology, HEMT is an acronym that stands for High Electron Mobility Transistor, which is kind of the fundamental device for both power switching and also RF amplification. This technology was, is considered established standard for defense applications, radar, EW, communications. It's becoming the technology of choice over silicon LDMOS for telecom frequencies above about 3 gigahertz, particularly for these massive MIMO active antennas, where high power efficiency that you get from GaN and across broad frequency bands, along with the small form factor you get, is a pretty big requirement. The megatrend here, I guess, is tapping into millimeter wave spectrum. So these are frequencies above about 30, 40 gigahertz, extending up to about 300 gigahertz for even higher data rates. And gallium nitride, along with other semiconductors like indium phosphide, for example, will become real enablers here.
Yeah, thank you. So I want to talk now Australian policy. So I'm going to ask a question of Steve. The Australian Strategic Policy Institute recently called for a $1.5 billion investment in the domestic semiconductor industry. What are Australia's strengths and where should we be enhancing and growing our industry and capabilities? And would 1.5 billion even enable us to do anything like this?
Okay, well, starting with the first question, I think all of us should be aware that Australia's semiconductor industry is fairly small, certainly on a global stage. And it tends to be kind of lumpy. We have certain areas of expertise in different areas, and they tend to be spread across the semiconductor value chain. And so pointing first at epitaxy, which we talked about earlier, on the industrial side, there are two significant players doing epitaxy, Blue Glass, and then Solana, where I was up until a couple of years ago. And then there's some work in Western Australia that's commercially focused or defense focused. And then there's a lot of epitaxy expertise spread across the universities as well. And in fabrication, we've had a fair amount of, it's still small on the global stage, but we've had a fair amount of semiconductor fabrication in the country. In the past, it's sort of fallen off in recent years. Solana, Bosch, and Motorola all had fabrication facilities which have now closed. But there's an optical manufacturer here called Finisar, and then of course, and there's a national organization called AMF, which has processing facilities at universities across the country. On the design side, there's expertise in RF, particularly at Macquarie University and companies that have spun out of Macquarie. There's some expertise in analog and digital, but very little on the assembly side. Looking further afield, Australia has invested very heavily in quantum, and I think has now developed a prominent profile internationally in quantum computing. And then there's a lot of work going on, primarily in universities, but also in some spin-outs in polymer electronics. So those are the areas where I would see some expertise. And in terms of a $1.5 billion investment, yeah, I think it would make a difference. I would spend it differently from ASFI, but I certainly see areas in which it could be profitably put to use. And in addition to building on strengths, I would also look at areas in which we should be developing new strengths. And really where I see the main opportunity right now is in what I call heterogeneous integration. This is where you combine chips made from different technologies, different materials into a single component. This allows you to exploit the inherent advantages of the different technologies, and you can achieve certain things you can't with a single technology. So you can improve overall performance because you can stack the chips on top of each other, which gives you much shorter wires connecting the chips. You can improve power, and you can also achieve a level of flexibility where you can mix and match different components in order to customize a semiconductor component for the application. So GaN would have a very natural role in that. So you can exploit the sort of characteristics of GaN that we've been talking about and combine it with silicon and other materials in order to produce a better overall solution. And so where I see the opportunity for Australia was really to invest in a commercially focused foundry, which would have capabilities in compound semiconductor device fabrication and in some of the components that are required for heterogeneous integration together with assembly and test. And to me, that you can actually start small. You don't need 1.5 billion. You could probably start with a very small, based on the analysis I've done, you can start with a very small sort of $60 to $100 million facility to get started. You need to establish profitability, identify the market, start building the business and industry within Australia, and identify the markets you really want to address on a longer term basis.
Yeah. You've answered my follow-on question perfectly, which was around, would building a GaN fab be a strategic asset in this country? And I think it's really important just to reiterate what you've just said, right? And this builds on what Ug said earlier around epitaxy, providing that, replacing so many of those steps so that the cost of building this kind of capability is an order of magnitude smaller than what building a silicon fab would be. And I just don't think that's truly well understood by policymakers in this country. So it's definitely worth repeating. I want to come back to you now, Ug, to ask you about IQE's foundry services, because you provide custom product development services to the industry. How do you collaborate and support players of all sizes? And are startups and SMEs critical for innovation?
I'll start answering the second part, which is about the innovation. Right? So startups and SMEs are certainly innovative by nature. I've worked in a few startups myself, and so I always say that every large company was small at least once. And IQE has also grown partly by acquisition over its 30+ year history, and we're smarter for it. Just one thing about startups and SMEs and innovation, part of it is in the structure of the team and the company itself, right? Because the life cycle of a startup company is dictated by major life events, right? So VC funds, exit strategy requirements, and that tends to focus the team on a problem or a smaller set of problems, with great education, be able to bring this to completion, so to speak. But also it's important to recognize that innovation occurs in mature companies as well. It tends to occur perhaps in more organized ways, in development projects, road mapping and such, but innovation can and does occur at any company size, I think. In terms of how we work with companies, for small companies or any companies, we try to engage as early as possible in a project, right? Such that we can form a mutually beneficial partnership. And look, everybody has limited resources, right? So by doing this early, we can support early product development. We can speed up qualification schedules during the project, and we can also ramp to high volumes, when the time is right for that. And so one strength of the Foundry model is that we can support short product runs, early on in the project when it's needed, and then we can later on ramp to high volume. And this, in many cases, avoids the need to purchase capital equipment, at our customer site, which is much more capital efficient across the board. So overall, it's an effective solution for companies, small and large, I would say.
Yeah, thank you. So how often do you
Yeah.
see disruptive startups acquired by established players? Fairly often.
Well, that's a good question. I think it varies, right, to some extent with the economy. We certainly have seen some of our partners being acquired, in some cases by another of our partners, right? It's a good and natural process. Hopefully everybody wins in the transition.
Love it. Thank you. Josh, coming back to supply chains, can you give us an overview of Blue Glass's laser manufacturing process and how you progress from atom to application?
Yeah, absolutely. I really like that phrase, from atom to application, because that's really how we think about making lasers here at Blue Glass. So look, we heard a little bit about epitaxy, but that's where it starts for us. So, we're making gallium nitride based laser diodes. So we have to start with atoms of gallium, atoms of nitrogen. We deliver them into our reactors, and we grow epitaxially thin semiconductor layers. And that really is an atom by atom process. We're not placing them individually. We don't think of it as an atom by atom process. We're controlling the environment. We're changing the pressure, the temperature, the gas composition. We're changing that environment to increase the probability that as those atoms arrive to this crystal surface, that they end up in the right location. And we're trying to get a high crystal quality. High crystal quality is key. We said earlier that it all starts with epi. Good quality device begins with epi, and that's really what the objective is. And then what we do is we modify that environment. So as we are depositing this thin layer, we change the composition. We add some aluminium, we add some indium, and we get these abrupt structures that we can grow. They're still very, very thin films, but we have vertical structure. The next step is to fabricate. So at that point, we have a laser wafer, we would call it, or an epi wafer. It has thin films with a vertical structure, but no lateral structure. And so the fabrication process involves adding that lateral structure. And typically this is done using photolithography. And what that really means is we put down a photosensitive layer. We expose that layer in certain areas, and it's called patterning. And that is able to protect one part of the wafer where adjacent to the wafer, we can do something. So we might etch away a section, or we might add a new layer, some metals, something like this. And throughout those fabrication steps, we're able to divide this large wafer into individual stripes that are the building blocks of our lasers. So small, thin, very, very small stripes, still on the wafer itself. At that point, we then need to divide the wafer up. Okay, so that sections this large wafer into small individual chips, sometimes collections of chips. And then we're able to put metal contacts or electrical contacts onto those chips. And fundamentally, we have a laser at that point. If we were to pass current through the device, pass electricity through the device, because of that unique structure that we began with in the epitaxial process, the electrons that go through during that process generates photons of light, and our unique structure traps those photons in this long strip. They traverse backwards and forwards on this stripe, creating more photons. So 1 becomes 2, becomes 4. That process sort of runs away, and that's the building blocks of lasing phenomena. At that point, though, it's not ready for application yet. We need to, these chips are small, they're fragile. We need to mount them onto something that protects them. So they are bonded onto something a little bit larger. That provides some structural integrity to the device. And it also provides an ability to pull heat out of the device. So we're putting a huge amount of current through a very, very tiny chip. It gets hot. And by bonding it onto this submount device, we can draw heat out of it. And then the final step is to package that. So that whole device is then encapsulated in a hermetically sealed environment. This is a small package, and that protects it from the environment and enables the device to run at high current for a very, very long time. So effectively, we began with atoms of gallium and nitrogen in some cylinders, and throughout that transition, we transform it into a small laser device ready for application.
Thanks, Josh. Actually, we're getting some questions about the supply chain. So I might put this one to Hugues. What are the critical dependencies in the supply chain for GaN? And are there less dependencies for gallium nitride production than there are for silicon?
That's a great question. So there's a few different ways to look at this. Critical dependencies. So you need buildings, equipment, things like that. So there is a supply chain for that. Materials, substrates, typically vary, right? So you can have sapphire, silicon carbide, even gallium nitride is a viable substrate, as Professor Van Baars knows very well. And so in some cases, substrates can be a constraint depending on the type of applications you want, volumes and such. In terms of processing equipment, maybe just to Josh's point, about the entire manufacturing process, the processing equipment, and Josh, you might comment as well, if I'm allowed to bounce a question. The processing equipment, generally speaking, is relatively available, right, for making devices and things like that in this particular area. And so there are really large fundamental constraints. One of the things is the qualification cycles can be long in this industry, right? So think about automotive, for example, or there are cases where time is a constraint. Time can be your enemy, and so there are cases where having a running start is really useful. So if you have buildings already facilitized, ready to load up more equipment, as opposed to building from scratch, as Michael was talking about the CHIPS Act. In some cases, we start from a green field as a brown field. So there are some constraints associated with that, depending on where we are. So compared to silicon, generally speaking, silicon will have much larger footprint, and much more expensive equipment. So that's one way to think about it. I think I don't know if anyone wants to add to this. Feel free to do so.
Thank you. We're also being asked, where does everybody source their gallium inputs from? You want to take that first?
Yeah, I can take a stab at it. There is gallium in various parts of the world. Some gallium comes from China, right? Some of you will have seen news that there are some restrictions on exporting gallium from China in some cases, but there are also sources outside of China that are sufficient, to operate in a commercial environment.
Yeah, I'll comment on it. Most of the metal organics we get are coming from Korea or Japan, which aren't getting restrictions on the gallium. Even the substrates are coming from Japan. So Japan is a key supply partner for some of the substrates here. But it's just a lead time issue. 4 weeks is typical. But yeah, there's been some independence now that China started to restrict the gallium, but they're not the only source of gallium, so they don't have a lock on it like they do on the lithium. Gallium is a byproduct of aluminum mining, so we can get gallium in the U.S. and even some of the metal organics are now still being made in the U.S. So I think the supply chain is pretty safe. And like you said, the machine, the process equipment, there's no limitations there for scaling.
Yeah, thank you. Yeah, I think that gives a lot of confidence to the supply chain stability. A question for you, Michael. Aside from the defense and consumer tech like fast chargers, when would we expect to see widespread adoption of GaN technology in data centers, etc.?
So that's a great question. I wish I knew the answer for sure, but I can speculate a little bit here. There are more commodity, high volume, low margin kind of segments where some would predict that to take place. You look at cellular handsets, for example, and there could be a time when RF gallium nitride, this would be on probably silicon substrates rather, could play a role there in the future. And then there's the high margin applications, lower volume, which are more dominant now. I would say across the industry, at least for the RF side. Not so much for the solid state lighting. That's more become commoditized for the consumer applications and things, and then there's GaN power, which is trying to head that direction as far as becoming more of a commodity. I think there's certain applications on the RF side where we're seeing potential for some price elasticity for very high data rate kind of cellular backhaul applications where they're holding out for basically the cost of the technology to come down. So depending on how you look at it, you can point to certain applications like I mentioned for the solid state lighting where it's already been adopted in a widespread way. You can get gallium nitride fast chargers and things like that. But time will tell beyond that.
Yeah, thank you. A follow-up question on the heterogeneous semiconductors. Where do you see, this is for Professor Dunbars, where do you see the biggest application for integrating compound semiconductors with traditional silicon?
Wow, that's a good question. So as Michael alluded to, several groups are looking at putting gallium nitride directly on silicon, not just for electronics, but for optoelectronics. But I see the next big breakthrough or market there is GaN on silicon, big wafers, 12-inch for power adapters and RF starts to look feasible here. The quality is looking good and the reliability is getting there. It's not as good as the stuff on silicon carbide yet, but for lower cost applications, it's definitely getting there. And for the power adapters, a lot of the GaN is already on silicon. Then in the optics arena, we're doing something called photonic integrated circuits. So there it's direct either wafer bonding or growth of gallium nitride onto silicon and employed in what's called silicon photonics. So we can make chips that are going to go into quantum computers. We can make chips that actually have displays on them or do AI communication. So I think particularly integrating the light emitting capabilities in the laser of GaN with silicon will give us the ability to do very high data rate transmission for some of these much more, we'll just say data intensive and energy intensive communications that you need.
Thank you. Yeah. Got one question for Steve, because it's pretty topical in Australia at the moment. We're talking about it a lot. The Australian and Queensland governments have sent a strong signal for a more ambitious and technological future, investing nearly $1 billion in a quantum computing pioneer. We are a global leader in quantum science. How do we improve our efforts to retain local innovation and talent and commercialize more semiconductor and quantum technologies onshore?
Well, first of all, I would say that in Australia, quantum is an unusual case where there's a sustained investment over quite a long period of time. And in my recollection, it's been like 24 years or so since the work first started at UNSW. And I haven't seen that sort of sustained investment in other areas. So first thing is, in order to achieve, to build an industry, to be able to retain local innovation and talent, you need to make a sustained investment. And unfortunately, that really needs to be supported by the government. There's just not, from a investor point of view, it's a lot of these technologies are very high risk and the potential returns are fairly long term. And so it really needs to serve government support. On the other hand, you don't want to rely on governments over the long term. So the focus has to be on using government capital to get started and then build industry on top of that. So getting the industry to a point where it can support itself as quickly as possible. And from my standpoint, this idea I mentioned before of having a domestic fab is a very attractive way to get started on this. Would provide a route to market for new Australian technologies. It had to be structured in the right way. We could talk about that if there's interest. And to me, that it's a very natural way to start. We can start small and then grow larger over time. And I think we can get it to a point of being self-supporting within a reasonable amount of time, within the attention span of the government, as an example. So that's what I would do.
Yeah, it does really highlight the benefit of sustained investment over a period of time to really deliver what can be huge economic benefits for a country going forward. So I think that Australia does need to learn the lessons from the quantum sector. So that was really helpful. Really interesting questions come through. So I do want to put this to the panel. I might actually ask this of Professor Dunbars. How many of the major semiconductor companies like the Intels, et cetera, of the world are investing in and developing gallium nitride technology? Is it all of them?
No, it's not all of them, but I'd say 75% have it on their roadmap. Some are a little further along, like Global Foundries has a dedicated GaN team. Other companies I can't mention the names of. In addition to semiconductor companies, all the major media companies that make, we'll just say the G companies, the fruit company, the guys, they all have GaN efforts going on AR, VR, and then the AI communications. So it's definitely hot in the development scale now. How fast these technologies get to market, 2 to 5 years, has been a very fast timeline because the lack of reliability concerns. It's a very reliable technology once you get it going. So it's a lot. So when I say 75%, there's a lot of semiconductor companies in China, Japan, Korea. So I'd say it's on the order of, it's approaching 100 companies for sure.
Wow. This has been such an interesting panel, and I could definitely go for another hour. And we have so many more questions. So what I'm going to do now is a lightning round wrap up from everybody. I'm going to start again with you, Professor Dunbars. You've had a luminous career. You've pioneered cutting-edge photonic technologies. What have been some of the biggest disruptors you've seen in the industry, and what do you think will be the next big catalyst?
Wow, that's a tough one. There's so many things to choose from. I mean, surely the power electronics is going to be big, but I think lasers for, blue lasers for communication and displays will be big, along with the ability to do quantum computing. It's going to penetrate a lot of markets because we don't have semiconductor lasers now in the blue and the ultraviolet, but we are getting them out to the market now. So that's a huge area. And I should mention, of those 100 companies, only 3 are working on blue lasers. So I think that's one advantage Blue Glass has. It's an early adopter here. And so that's where I think the next breakthroughs are going to be.
Thank you. Your turn. The world is unlikely to be able to meet its carbon emissions reduction targets and achieve net zero goals without GaN. Can you tell us more about the role GaN plays in decarbonization and digitalization?
Yes, sure. So, in decarbonization discussions in the last couple of decades, actually, right, the time flies, right? So we've been hearing continuously that we need all of the above, right? So energy efficiency, right? Renewable generation, energy storage, grid resilience, and such, right? And gallium nitride essentially either is or can be a part of the solution for essentially all of these power management applications. We talked about power bricks already. We talked about data center powers. The one application I think we didn't talk that much about it, but it's electric vehicles, right? At least in the US, we're still waiting for more models of affordable electric cars.
Mhm.
So once GaN starts to get a little bit more into the various parts of the car, right? So onboard charging, DC-DC traction, etc. We should continue to see price reduction, and that will, in turn, will drive adoption of more electric vehicle that goes towards decarbonization. We talked about data center already. Display is a big one, as Professor Dunbar's mentioned, as well as Josh. So there's multiple places where GaN will play a key role, I think, for decarbonization and digital. Right?
Thank you. Michael, how has the GaN market changed over the past decade, and where do you see the key sector trends in the decade ahead?
As the panelists know, it was the invention of the blue LED that first led to commercialization of GaN-based solid-state lighting at Cree in the early 2000s, and then that company, who later became Wolfspeed, which now happens to be part of MACOM, began volume production of GaN MMICs in 2008, along with other companies around that time. And then, going back about 10 years, GaN was just starting to penetrate the defense market, and its commercial use was quite limited, especially on for the RF applications. But today, GaN markets are split, as we've mentioned, between opto, power, and RF, where GaN power switching device companies are trying to displace the silicon power MOSFETs and silicon carbide power MOSFETs and applications up to about 600 volts. GaN for RF really has no rivals, I'll say, at K-band frequencies, which is about 30 gigahertz and below, where very high efficiency is required. The RF segment is expected to grow to the tune of, say, roughly $2 billion by around the 2030 timeframe, with big gains in both the defense markets and the cellular infrastructure markets, including adoption of next generation or more advanced node. Read that as the highly scaled gallium nitride processes into higher frequencies than what it's currently offered at. So in the millimeter wave frequencies. So that would be the trend.
Steve, where do you see GaN semiconductors changing how we use and interact technology going forward?
Well, just based on the applications I've been working with over the years, I think it has a very immediate effect. I mean, some of the applications are very tangible to people. So as an example, the idea of being able to use point of use detectors to detect diseases, or to for the sterilization applications, or things that people could use on a regular basis. I mean, it's a much more tangible, immediate, I think, interaction with the technology that's being enabled by GaN.
Yeah, it's perfect. And finally, Josh, could GaN become as crucial to the semiconductor industry as silicon?
Well, I mean, I think it already is. I think we've heard today that, it's going to infiltrate various aspects, many aspects. It's already used in commercial lighting. It's used in automotive lighting. It's used in manufacturing. Think of the example of the electric car that we were just discussing. It can be used in the power transfer. It can be used in the headlights. It can be used in the manufacturing of some of the metal components, the manufacturing of the copper aspects of the battery. And this is all sort of in a kind of a clean energy umbrella. No clean energy roadmap could exist without gallium nitride on it, right? And that's not even to mention all of the other cool applications, the quantum applications, bio, visual communication, the list goes on. I'd have to say that it already is.
Love it. I think that is the perfect way to wrap it up. Look, thank you all so much for sharing your insights and expertise with us today. It has been such an interesting discussion. I have learned so much, and I'm already somebody who has, as anybody who's ever met me, is fairly passionate about gallium nitride, and even I am just more excited after today's session. So thank you so much. I'd also like to say thank you to the event organizers, Blue Glass Limited and Share Cafe, for bringing these educational series together. A recording of this webinar will be available from both the Blue Glass and Share Cafe websites in the next couple of days. And if you've missed out on any of our previous webinars on the global semiconductor industry, Australia's place in the semiconductor world, and the strategic might of lasers for the defense sector, please check these out on our website also. We look forward to bringing you our next expert panel, this time highlighting the future of quantum intelligence and Australia's role in the quantum revolution. Most especially, though, thank you so much to our amazing audience today. We look forward to seeing you again next time. Thanks, everybody.
Thanks.
Thank you.